Well, thank you very much for the opportunity to present my work. This is probably a situation with thinking outside the box, like what Jojo said earlier, and then probably a situation where thinking outside the box sometimes causes problems. Actually, when my postdoc mentor always talked to me, complained about me, saying that this is about PARP. He said, "Oh my God, always work outside you don't work on PARP or poly-ID polypolysylation. You work on the periphery of PARP." So I made a career out of it. So PARP inhibitors are now being used in a number of cancers, but primarily BRCA1 mutant, whether it's ovarian, breast, and other type of cancers. There are about 5. Actually, I'm citing on the total 4. But there is a 5th PARP inhibitor. But what you can see here, and I see. What you can see here that all the PARP inhibitors are being used at very high doses. They have to be used at high doses, and I can explain that in a minute. But the principle for using PARP inhibitors in these cancers is really related to the DNA repair, the mechanism of DNA repair. In normal cells, for example, you see here, normal cells that has ability to repair DNA with homologous or combination, and that's a primary pathway, but also relies on PARP. But when you have a cancer cell that is deficient in BRCA with the BRCA mutation or BRCNS, these cancer cells rely heavily on the PARP pathway. So if you use PARP inhibitor, you have this fascinating situation where you are putting the cancer cell in a corner with inability to use alternative pathways to repair the DNA. So they end up with accumulating a large amount of DNA damage, DNA double-stranded breaks. And these large levels of double-stranded breaks are fatal and cause cell death. And this is what the concept of synthetic lethality. But one issue with the DNA repair enzymes, not only PARP, but many other DNA repair enzymes, you don't, for somehow, nature designed these proteins that we need only a small portion of these proteins to achieve DNA repair. So clinically, you have to inhibit almost 100% of let's in this case PARP. So you have to use very high doses of PARP inhibitor. So this is obviously every time you use something close to MTD. And most of the PARP inhibitors are used at near MTD, or maximum tolerated dose. So you end up with having a lot of side effects, but also the classical issue with development resistance. A lot of pathways, we don't know the mechanism. There's only one way that we understand with the mechanism of resistance, but in general, we don't know. Clinically, we don't know what happens in patients. We know what happens in some of the in vitro systems, but we don't actually understand the mechanism of resistance such a way to develop new drugs to avoid this issue. But like I told you, I think outside the box, and I've been always working on the periphery of PARP. So for many years, for more than 20 years, I've been working on what does PARP do other than DNA participating in DNA repair. So what we did is, okay, because for DNA repair, you need very little. So to inhibit DNA repair, you inhibit everything. So for us, we took a PARP heterozygosity approach. So when you have PARP heterozygous, whether it's mice or cells, these cells or these mice express about 50% of the protein, mimicking like a partial PARP inhibition. And also we could use low doses or low concentrations of PARP inhibitors, so mimicking partial inhibition of PARP. And with this, we were able, I think we have about probably 40 papers or so talking about that these partial inhibition of PARP can be anti-inflammatory, can protect against atherosclerosis, asthma, acute lung injury, diabetes, and many, many other things where DNA repair or DNA damage is not very, very important. But in the context of cancer, so we explored this in cancer. I'm not showing you a lot of data, I'm just telling you a story. So here, so we found that partial PARP inhibition, and here when I talk about partial PARP inhibition, we are using sub-IC50 concentrations or doses in mice and in vitro. And we use gene heterozygosity as a model, as a genetic model, which is clean, no drug being used in the system. And what we found is that the partial PARP inhibition is very much more effective at reducing tumor burden in colon. The one we published was colon cancer, but we have data with breast cancer and lung cancer as well. So we found that there is this low partial PARP inhibition is more effective at reducing tumor burden in these models, while total PARP inhibition here using very high doses. Let me just give you an example. We use 0.2 milligram per kg in mice, or that's a 4 nanomolar in vitro. IC54 PARP, like olaparib, is about 5 nanomolar in vitro, and about 30 in people who use olaparib in cancer settings. The starting dose is about 30 milligrams per kg. Remember, we use 0.2 milligram per kg. So we were able to see very, very nice effect with these partial PARP inhibition, but with the total inhibition with knockout, sometimes we see less protection, or sometimes when we use APC-min model, we see actually an aggravation with the PARP knockout. So the partial PARP inhibition is absolutely a lot more superior than complete inhibition. So we did, of course, I know we're scientists, we do mechanisms and things like that. What we found that these low doses or low concentrations of PARP inhibitors change the function of these MDSCs, these myeloid-derived suppressor cells. These cells are very, very important to maintain tumor genesis, to maintain the growth of the tumor by simply suppressing T cell function. So we were able to see that these very, very low sub-IC50 concentrations of olaparib in this case, or we tested other PARP inhibitors, that it reduces the function of these, or the suppressive activity of these MDSCs, allowing the immune system to attack So what we did, we combined it with immunotherapy, with anti-PD-1, anti-CTLA-4. We see an incredible synergy between the two. And recently, the first one we published, this one is about to be published. We found that the PARP inhibitors can decrease PD-L1 expression on human PBMCs, as well as dendritic cells and others, or cells that were derived from the bone marrow. We also, what we found is they also decrease the activity of MMPs. MMPs are very, very important for metastasis, as well as tissue inhibitors. They increase the levels of TIM2. These are inhibitors of MMPs, leading to a more stable micro or matrix within the primary tumor. Also, what we found that iniparib, which is actually the biggest fiasco, the biggest scandal with the PARP inhibitors, where I don't know if people know about this one here, but Sanofi spent about close to $800 million on this drug until it failed at phase 3 clinical trial. And then we found out that actually it's not a PARP inhibitor. So it was abandoned. So I don't know, by chance, we used it we had it in the lab, and we used it on human PBMCs and human and bone marrow cells. dendritic cells and macrophages and MDSCs, and we were able to see that it behaves exactly like a PARP inhibitors, and in such a way that it decreases the levels of PD-L1 and increases the tissue TIMs. So what we think here, that we have an alternative to using PARP inhibitors at a completely different, the other side of very, very low doses, in such a way that you can benefit drugs that can, anti-cancer drugs. You can, obviously you cannot use it as a single monotherapy, but you can combine it with a lot of drugs that could affect the immune system and affect or metastasis. And I think I stop here. This is, like I said, it's not really limited to colon cancer or breast cancer, but we can do a lot of other cancers. And in APRIB, again, about $800 million were spent on it to be shelved, to be on the shelf. Now I think we could resurrect this drug to be used in the clinic, and I stop.